ahead. So good afternoon, everybody. I'm Alessandra Azzollini, a PhD student under the supervision and in the group of Professor Sara Buson at the Würzburg University. And today I would like to present you the current PhD project that I'm working on, which is funded by the ERC starting grant, and is a study of the physical properties of the engines of neutrino-emitter blazars. So first of all, I will give a brief overview, which will probably be a refresh of what we've already extensively seen, both this morning and before. And then for the context and the motivations behind my work, and then the approach that we decided to use. So first of all, the main motivation behind my work is to try to give a contribution to try to solve the puzzle of high energy astrophysical neutrinos. As we've already seen in these days, they are very important, but also elusive particles to study our world, our universe, because they are nearly massless, and also they barely interact with matter. So on one side, they carry, this is important because they carry within themselves information about the position and direction from which they are originated. But on the other side, it makes it even more challenging to detect them. Also, they are important messengers because they are indirect probes of cosmic rays, because they are produced as byproducts of they are believed to be produced as byproducts of processes that involve also the acceleration and production of high energy cosmic rays. The instrument that is currently with the best sensitivity available to detect neutrinos is the IceCube Observatory, which is shown here in the structure, and it's located at the South Pole. An example of a map of data published by the collaboration is instead shown in this picture. I will not give in further details about this part because actually it will be addressed better in the next talk by my colleague, but I would highlight especially 2 points which are important for our work, which is the fact that it's still currently under debate, which are the astrophysical sources that are able to produce neutrinos, and also in which processes they originate. In the recent years, growing evidence has been put forward towards the connection between neutrinos and AGN. The first, as we've seen also before, has been the Blazar TXS 0506 class 056, and the other two shown here are also AGN. So let's try to focus on this class of objects to understand what they are and why they were able to produce neutrinos. No, what have I done? Okay. So active galactic nuclei, AGN, are the compact central region of active galaxies. The currently most accredited model is the so-called unified or unification model, according to which different classes of objects that fall within the definition of AGN are actually the same kind of object, but which show different observational properties, and in particular, different inclination angles. The blazars are specifically those in which the relativistic jet is pointed towards the direction of the line of sight of the observer, and are the objects on which I will focus from now on. Blazars in particular are characterized by the presence of a supermassive black hole in the center, which accretes mass through an accretion disk from which it is surrounded, and in this region it's also believed to be present a hot corona. This central part is surrounded by a torus of molecular dust, which is called the dusty torus. And in this structure, the accretion of matter onto the central core is able to create the conditions in this kind of objects for the launching of the relativistic jet. The observed radiated emission of the relativistic jet is highly Doppler boosted. It is able to span the whole electromagnetic spectrum, and is also able to photoionize and interact with the clouds of dust and gas, which are present closer or farther out away from the central region, which are the broadline region, closer, so at higher velocities, or the narrow line region, which is farther out at lower velocities. In particular, for our work, we are interested in studying the class of radio loud AGN. In particular, they are traditionally classified in the two subdivisions of flat spectrum radio quasars, FSRQs, and the BL object.
Sorry.
Sorry. Okay, and they are historically classified according to the observed properties, in particular on empirical taxonomy, on the basis of the presence of lack of emission lines in the optical spectrum, but also the properties like the inclination angle of the jet, also luminosities in other bands, redshift, accretion modes and efficiencies, or also the properties of the central black hole. So, to study blazars, an important tool, an important proxy is the so-called spectral energy distribution, the SED, which is the trend of the energy flux as a function either of energy or frequency. An example here is shown for TXS, and in particular, the interpretation in the leptonic scenario of the SED of blazars can explain the double lambda shape that we can see in the trend. The first peak usually falls at lower energies and is believed to be produced by synchrotron radiation of the population of accelerated relativistic electrons inside the jet, while the second hump falls at higher energies and is produced by inverse Compton radiation, either self-Compton or external Compton. The leptonic scenario is able to interpret well the SED of most blazars in the universe, but sometimes it has to be complemented with a leptodronic or hadronic scenario if we consider also the presence and acceleration of hadrons in addition to leptons. And this is also the framework in which it can be predicted and expected the presence of neutrinos, which are highlighted here in the SED of TXS. So in our work, we will focus on a selected subsample of blazars that are 52 and are taken from the 5th edition of the Roma Visicat catalog. In particular, they were selected through a positional cross-correlation analysis between IceCube data and the Visicat catalog. A particular feature of the Visicat catalog is that the distribution in the sky of the sources is shown here in the picture, is that the blazars are selected without any preference towards a wavelength band or survey strategy. So in this sense, it is not biased. In our sample, we have 10 sources located in the southern celestial hemisphere and 42 in the northern one. They are highlighted here with the squares in the IceCube neutrino method. Our goal is to try to inspect the properties of these sources, in particular using a multi-wavelength approach. The main part of my work is based on the analysis of the optical spectroscopy data of these blazars. So what we've done first was to use proprietary data. We observed the sources that were not available in public archives. In particular, we used the telescopes like VLT or Gemini South, and we complemented this information from the ones that were already available, for example, from the SPSS survey in which the spectra are taken with the APO telescope. Optical spectroscopy can probe the accretion properties of the systems, but it's also a very powerful tool because, first of all, it can allow us to estimate the redshift and therefore the distance of the sources. As I said before, it's also the traditional way of separating blazars into FSRQs and BLX through the intensity and the width of the emission lines in the spectra. Two examples of optical spectra for two sources in our sample are shown here. For an FSRQs in which the emission lines are evident in the spectrum, while the one of the BLR appears featureless. I am particularly interested in the emission lines that are produced in the BLR, thanks to the radiation that coming from the accretion disk photoionizes the gas in the BLR, and in particular in the hydrogen transition of the Balmer lines H alpha and H beta, but also more highly ionized species like carbon-4 of magnesium-2. And in particular, in this FSRQ, we can see both these transitions. They are important because they allow us to estimate the physical properties of the central engines, like the luminosity of the BLR, of the disk, but also the volumetric one, and also more intrinsic properties like the mass of the central black hole, through which we can have an estimation of the Eddington luminosity, and also the sizes of the central regions through the radii of the BLR and the dust torus. Then we complemented the information coming from the optical by taking information in radio and gamma rays. In particular, BZCAT provides the value of the radio power at 1.4 gigahertz for the two surveys, FIRST and MVSS, and this is the sky coverage of these two surveys. And I've also taken instead the information about the gamma from the third data release of the Fermi catalog. In particular, I estimated the gamma luminosity in two different approaches. For the sources which were detected, I took the flux and then the luminosity from the catalog. And instead, I placed an upper limit using the Fermi lattice sensitivity for the non-detected sources. Both radio and gamma are important because they give us a proxy for the intrinsic power of the relativistic jet of blazars. So the approach that we decided to use was first, I collected the data and information from both the public archives and from the literature. Then we asked, and we were granted also for observational times with optical telescopes, thanks to proposals that were accepted. So I performed the reduction of the proprietary data of the spectra that we observed, and then they were included in the sample taken from the public archives. So I inspected visually the presence of emission lines in all the spectra. To fit them also with the Gaussian profiles in order to obtain information that were useful for further analysis. For the spectra that looked featureless, I estimated upper limits on the flux in order to have an idea of the quantities into play. Then all this information were used to estimate the physical properties that I mentioned before. In particular, we were interested in the estimation of the accretion rate expressed as the BLR luminosity or the gamma luminosity in Eddington units in order to be able to compare objects with different black hole masses. And I performed a tentative classification of the sources themselves. We are currently at the last stage, which is the interpretation of all these properties and all these results in order to understand which are the physical properties that could make this subsample of blazars able to produce neutrinos. So to summarize, we've seen that high energy astrophysical neutrinos are very important messengers and particles because but their origin is still unclear. Among the candidates, AGN looks very promising in this sense. So right now my work is focused on a selected sample of blazars that we are analyzing with a multi-wavelength approach to understand what makes them able to produce neutrinos. A lot of work, of course, still has to be done, but for now, from my side at least, this is all, and I thank you all for the attention.
Thank you, Alessandra. We have questions. I had a question on the last slide. You had so the last step where you are trying to use then this data that you extracted. So how does this work in practice? Are you looking into neutrino alerts, very energetic neutrinos, and try to find what sort of properties are correlating with these?
There is an interpretation on the properties of the blazars themselves. Mm-hmm. So, but it's still a work in progress. So I'm focused on the blazar part more than the neutrino. The neutrino, okay. Yes.
Okay. Yeah, there's one question. Yeah.
A little bit in the same line. Are you looking in the end to do like a global fit of all the? Are you looking to do like a global fit of all the wavelength at the same time?
Yeah, we are still. Let's see. It's also a future perspective probably. So for now, yes, we are. For now, my work has been only focused on optical, radio, and gamma. So, but yeah.
Maybe.
So,
okay.
maybe.
Sounds good. Thank you.
Thank you for the question.
Other questions? Okay. Then thank you, Alessandra.
Thanks.
It was a very nice talk.